we just have one, but I don't think let's do it. There's going to be one new topic on it, just circular motion. Okay. So exam 4 is going to be a week from today. Yeah, like no one wants to have to study like over Thanksgiving. Let's just do it, right? That's what I thought. So that's a week from today is the 21st. Just the final. Yep. But there's a lab test the week we get back from Thanksgiving. I know. I don't know. What am I supposed to do? I know, but there's only so many days and weeks. Okay, so exam 4 is next Tuesday, and the topics are everything up through circular motion. Yes. I don't know, but as soon as I can get them back, I will. That I promise you. The same time as that, when I can. As soon as possible. I want you to know that every day that I don't get it back, I feel worse about it. It'd be nice. I'll see what I can do. And then lab exam 3. Oh, before I say that, here's the good news. No labs next week. For Thanksgiving. And then lab exam 3 is in lab the week of so that's like the week of 11/27 to whatever is 4 days after that. Anybody have any questions about any of the stuff coming up? Yes. This is the last lab, yeah. So then there's nothing next week because of Thanksgiving. The week after that is the lab test. And then the last week is just that half-hour post-test that it doesn't count for your grade, but it's just sort of to see how well you've picked up these intuitive things. It's really for me. And so, excuse me, I'll give you a little bit of extra credit for taking it because I want people to come and I don't have any leverage left, you know? So the day class, well, first the night class is Monday, December, I think that's 11th at 6 p.m. in S1326 next door. And the day class is not Tuesday, Thursday. That'd be 12/14 at 2 p.m. in S1328 right here. And you don't have to tell me ahead of time. You can just show up to whichever one of those works best with your schedule. So if you feel ready on Monday and it works better for your schedule and you can clear your schedule and come on Monday, you can be done with the class then. Any other questions? Okay. Well, let me do, I'm going to do one more circular motion example. This one will have some non-uniform circular motion in it. And then the last thing I have to talk about is the very specific case, tetherball problem. And then we're done with circular motion. So here's the example. Let's say there's one of those playground carousels. You know what I'm talking about? So it's like spinning this way, and this kid's like, why did I get on this? And let's say that this kid has a mass of 15 kilograms. Let's say that the speed of the kid is 3 meters per second. And let's say the radius of the carousel is 2 meters. They don't put these in parks anymore because they hurt kids really badly. And actually, we found one of these at a park where my son had baseball practice, and we went and played on it for like 42 seconds before he and like 2 other kids fell off and like hurt their heads and stuff. And so the question we want, so here's what we want to find out. So first, we're going to do this. If the speed is constant, what's the acceleration of the kid? No, because he's turning. So there's still going to be a centripetal acceleration. Speed, that doesn't make any sense. Kid. Second, so assuming that the speed is constant, what's the horizontal force required so that he doesn't fall off? If you look at this picture, by the way, what would be providing the force, the horizontal force that would keep him from falling off? Yeah, that's right. Butt friction. Or possibly pants friction. You can't really tell from the picture. And then third, so now we'll say that the speed isn't constant. So let's say that if he's speeding up, at a rate of 10 meters per second squared, what's the acceleration? We'll do both of these again, acceleration and horizontal force. Well, this is not a tetherball problem, so we're going to choose a view where we can see the circular path. So for part A, there's the circular path. This is a top-down view. The coordinate system is like this. And now we have to choose a point on the path that we're going to do the calculations for. I can't remember what we've done. Let's do it here. I just keep moving it around so you can see how that affects things. And now we draw a vector from the point we care about towards the center. That's the direction of the centripetal acceleration. The magnitude of the centripetal acceleration is the kid's speed squared over the radius of the circle. So that is, what did I say the speed was? 3 meters per second? Okay, so 3 squared divided by 2. So 4.5 meters per second squared. And then the centripetal acceleration is pointing in the negative y direction. So as a vector, that's 0, negative 4.5. For parts A and B, the speed is constant, so there's no tangential acceleration. And so the total acceleration vector is just 0, negative 4.5. Any questions about that? Part B, now we want to calculate the horizontal force required for him to continue making. So if he doesn't slip off, what it means is that he maintains that acceleration. So we'll assume that that's his acceleration, and we'll use Newton's second law to calculate the force required to maintain that acceleration. So first we have to draw a free body diagram. So a free body diagram of the kid from a top view. I'll just draw it like this. I don't know. That's his head. Okay, so what forces are acting? There is a weight, but it's not in this plane. There's also a normal force pushing out of the page. That doesn't show up in the plane. So the only forces are the unknown components of the horizontal force. So I'm just going to write it as, we'll say there's an Fx that way and an Fy that way. And then Newton's second law says this force vector, and I'll just call it Fx, Fy, is equal to the mass of the kid times the kid's acceleration of 0, negative 4.5. And so the x equation says fx is equal to 0. The y equation says fy is equal to 67.5 negative. Is that right? And so then you can put those together and say that horizontal force altogether is 0x negative 67.5 newtons. Any questions about that one? So is that uniform or non-uniform circular motion? Uniform is when it's constant speed. So now we're going to do a non-uniform one because we're told that he's speeding up. So for part C, I'll just keep everything the same. This is the direction of the centripetal acceleration. It's rotating this way. So first, the centripetal acceleration, that's going to be just like it was before. We didn't change anything. 0, negative 4.5. But that's not the question. Yes, thank you. Okay, so that's the centripetal acceleration is still the same, but now there's a tangential acceleration because the speed is changing. So we have to think about the tangential acceleration. We know it has a magnitude of 10. So in order to do that, we have to think about the direction of the velocity, think about whether it's speeding up or slowing down. Now, what direction is the velocity vector? Ow. Yes, that's right. Oh, it was worth it. Okay, so there's the velocity. Then is he speeding up or slowing down? Speeding up, so the tangential acceleration is that same direction. So A tangential, is that in the positive or negative x direction? Negative. So this is equal to negative 10, 0 meters per second squared. And so now the total acceleration is 0, negative 4.5 plus negative 10, 0. So negative 10, negative 4.5. And now that we know the total acceleration, we can go towards Newton's second law. So first we have a free body diagram. That looks just the same as it did before. We just have those horizontal force components. So Newton's second law now says Fx, Fy is equal to 15 times the total acceleration vector, negative 10, negative 4.5. So fx is equal to negative 150. Fy is equal to negative 67.5. And if you combine those together, the total horizontal force is negative 150, negative 67.5 newtons. So which one of those two cases is he more likely to slide off? The uniform case or the... So the second one has a bigger force required. You could figure that out if you took the magnitude of that force. You know, the square root of the sum of the squares. You'd see that this one's a lot bigger. I mean, you can just see it's a lot bigger because it has the same component as the other one and then has a whole bunch more. Any questions about that? Okay, let's do another one actually. So let's say this time so there's a string that this person's holding with a mass on the end, and you know, it's moving in a circular path. And let's say the string length is 0.2 meters. And the mass of this object is 0.1 kilograms. And let's figure out the tension in the string at 3 points. So let's say A, B, C. I'm not even going there. I'm too mature for that. Jorts. It sort of looks like Gru. Okay, so you need to help me figure something out here first. Let's see. So let's say at C, so V, let's say the speed at C is 5 meters per second. And then that means that I'm not, you don't have to pay attention to how I'm doing this. We'll talk about this stuff later, but God. I just broke this table. Yeah. Let's see. So that means that at B, tell me tell me, oh, 25 over 2, 12 and a half. Okay, so you don't have to tell me that. 12 and a half, so 9.81 times 0.2 plus v squared over 2 is equal to 12.5. Can someone calculate what v is there? The positive value of v? What? That can't be it. Okay. 4.59 meters per second. And then at A, we have 9.81 times 0.4 plus v squared over 2 is equal to 12.5. Can someone calculate that? .14? 4.14 meters per second. Okay, so if you were swinging this thing around so that at a speed where at the bottom it was exactly 5 meters per second, and these would be the speeds at points A and B. 4.14 at the top, 4.59 at the middle. And let's calculate the tensions at all three of these points. So what's the cable tension, the string tension? At A, B, and C. Okay, so first A. First of all, is this a tetherball problem? Well, it can't be because I haven't told you how to do tetherball problems yet. There's an easy way to just do those. But what distinguishes this from a tetherball problem? Direction. So it is like tetherball in that this is only connected to a string and it's being swung around in a circle. But in tetherball, it's going around a circle that's parallel to the ground. This is going sideways like that. And so that's the difference here. So the first thing we have to do is choose the view. And this is one where we don't get to choose where on the circle we're looking at. We're doing the point A, so that's up here. The centripetal acceleration is like this. The magnitude of the centripetal acceleration is 4.14 squared divided by the radius of the circle, 0.2. So what do you get for that? $85.69870. meters per second squared. .50. It was 85. 85.70. Okay. And that's in the negative y direction. So centripetal acceleration vector is 0, negative 85.70. At this instant of this motion, is this speeding up or slowing down? We talked about this once in lab. Remember, the only thing making it, well, in this case, it would be slowing down whenever it's going up and speeding up whenever it's going down. At the top and the bottom, those are the 2 points where it's not going up or going down. And so there's not going to be any tangential acceleration at those points. Just at those instants, it's not changing speed. Remember that from lab? Okay, so tangential acceleration is 0. So the total acceleration vector is just 0, negative 85.70. Not the whole way around the circle, but just at that instant it's at the top and the instant it's at the bottom. You can think of it as like in the little tiny amount of time surrounding the top and the bottom, the speed is constant. So now we have to draw a free body diagram. What are the forces acting? There is string tension. Is there weight in this case? Or is that out of the plane? There is weight unless you're picturing him lying on his side. That's not what I meant. So the weight is 0.1 times 9.81, so 0.981. And then the string tension, which way does that go, up or down? Down. So now Newton's second law says 0, negative t plus 0, negative 0.981 is equal to the mass times the acceleration vector, which is 0, negative 85.70. The x equation doesn't give us anything, but the y equation says negative t minus 0.981 is equal to negative 8.57. And so, can someone tell me what t is? Yeah, 7.589, and it actually would be positive, I think. Okay, so the cable tension at the top of the circle is 7.589. Any questions about that one? Yeah. Point A at the top. Yep. That's why the cable force is going down. So now we're going to go on to B. At B, there's no reason you would know this, but I'm just going to tell you that the tangential acceleration, well, let me say it like this. At this point, it's speeding up at a rate of 9.81 meters per second squared. Do you have a feel, like, who thinks the cable tension at that point B, when it's on the side here, is going to be bigger than the cable tension at the top? 2 people. Who thinks it's going to be smaller? 3 people. Okay, that's 5. That checks out. That's everybody in the class. Total of 5 people. Okay. Okay, so we'll go through the whole process again. Here's the view. Now the point we're looking at is this one. The centripetal acceleration is this way. The magnitude of the centripetal acceleration is v squared over r. And this time, we're told that at B, the speed is 4.59 meters per second. So 4.59 squared divided by 0.2. What do you get for that? 105 point what? 34 meters per second squared. That's pointing in the negative x direction. Wait, which way am I? Okay. So it's in the negative x direction, so the centripetal acceleration vector is negative 105.34 and then 0 meters per second squared. And this time it's speeding up. It's rotating around the circle that way. Which way is the velocity vector? Down, yep. If it's speeding up, which way is the tangential acceleration vector? Yep. And it has a magnitude of 9.81. So the tangential acceleration, that's 9.81 in the negative y direction, so 0, negative 9.81. So the total acceleration vector is negative 105.340 plus 0, negative 9.81. And you get a total acceleration of negative 105.34, negative 9.81. And now a free body diagram at that point. Which way does the weight act? Down. That's 0.1 times 9.81, so 0.981. Which way does the cable force act? Yep, the center of the circle is this way. And so now Newton's second law says that t is in the negative x direction. So negative t 0 plus 0 negative 0.981 is equal to 0.1 times negative 105.34 negative 9.81. The x equation says t is equal to positive 10.53. And the y equation doesn't let us solve for anything. It gives us a true equation. So that's good. If it didn't give us if it didn't let us solve for anything and the equation it gave us was false, something went wrong, like we made an assumption that isn't going to work or something. But this tells us negative 0.981 is equal to negative 0.981, so that's good. Okay, so up at the top, the cable tension was 7.59. At the middle, the cable tension was 10.53. So bigger or smaller? Bigger. And what do you expect to happen at the bottom? You think that tension is going to get bigger or smaller? Yeah, it's going to be the biggest at the bottom. So there's the view. Here's the point we're looking at. There's the centripetal acceleration. The magnitude of that is 5 squared over 0.2, which is 125. That's in the positive y direction. So the centripetal acceleration vector is 0, positive 125. The tangential acceleration, just like it was at the top, is 0. At that instant, it's not changing speed. So the total acceleration is 0, positive 125. And now free body diagram. The weight acts down. Which way does the cable tension act? Up. Yep. And then Newton's second law says 0, positive t plus 0, negative 0.981 is equal to the mass times the acceleration vector, 0, 125. So the x equation says 0 equals 0. The y equation says t is equal to 13 point what? 41? 482? 81. Yeah. And this is how it always works with, if you just have something swinging around in a vertically oriented circle like that, and it's just hanging from something, like just just a tension is making it go in this circle. The tension is always going to be smallest at the top, biggest at the bottom, and in between the rest of the way. So what that means is if you have a cable that, say that you have a string that can only withstand let's say 11 newtons of force, it would make it fine through the whole rotation until it gets back to here, and then the string would break. And at that point, if the string broke when its velocity was this way, it would start with a velocity like that, and then fall, like free fall, in a parabolic path. If you watch, maybe, I don't know if we'll have time to do this, but if we don't have time to do it, you should go to YouTube and do this because it's funny. It's not so funny when it's you, I know that much. But if you go to like men's high bar wipeouts or men's high bar, whatever, falls, fails, whatever. So they do these crazy tricks, which I don't know what that's like. I used to do gymnastics when I was young, but I was not very good. But they do these crazy tricks where they like flip over the bar, do all these flips, and then re-catch the bar with their hands. Okay, have you ever seen that, like on the Olympics or whatever? It's incredible. But the thing is, like, you can only make it happen within a certain margin of error, And so there's a couple of things that can happen. Let's say it's two different things that can happen. The first one is you finish your flip, look for the bar, and it's too far away from you, and you can't grab it. Okay, so and then they fall down to the mat. It looks pretty dramatic, but those don't usually hurt that much. They just sort of land on a big soft mat, flat on their stomach or flat on their back. They deal with a lot more painful stuff than that. But the other thing that can happen, and that's related to this, is they do their flips, they reach out for the bar and just manage to catch it. But they're not all the way on, They're sort of on their fingertips. And if they catch it on their fingertips, if they're smart, or if they sort of catch it, and before they get to the bottom, they just let go and just fall down, land on their feet or land on their butt or whatever. But if they think like, I'm going to hold on, and they don't quite have enough of a grip to hold on, they come around, hanging on with their fingers. Their fingers are enough for them to make it all the way down to the bottom, but the tension keeps increasing. And down here at the bottom, their fingers are ripped off the bar, and they go flying and flipping horizontally, do like 1.5 flips, land on their head like 20 feet away or whatever. Okay, let's watch it. But not all of these do that. Okay, so look for those. Those are the 3 possible outcomes. They just totally miss it, like they just can't hang on. Or else they kind of grab on, but you'll see them purposely let go. Like, I'm not falling for this one again, And then the other one is so maybe a quarter of the ones that we'll see are them just peeling off the bar at the bottom and whatever, because that's where the tension is high. High bar wipeouts. I think this was the one that was better. Ooh, Red Lobster.
Endless Shrimp is back at Red Lobster right now.
We don't really need the sound. Okay, so that's one where he just missed it, you know? It looks pretty dramatic, but I don't think they usually get hurt doing that. I don't know, that might be a separate category. That was different. That wasn't a release move. That was just letting go at the wrong time. Hey, Gophers! Look, Minnesota Gophers there. Ooh, he just missed it. Oh, well, that was sort of it, you know? Um, that was like, I don't know why he didn't have a good grip, but you saw him peel off at the bottom because, and he just goes flying horizontally because that's where all the tension is required. Yeah, he could have pretended that was his dismount. Whoop, just put his hands up. That wasn't so bad. That could have been a lot worse. That was it. Like anytime you see it happen at the bottom and they take off horizontally, it's just their hands getting ripped off the bar. So that guy, I think that was sort of a bail. Like he, oh,
Want Epke deed die finale. Oh, en ook Boy is uit balans. Versneden. Even kijken. Hij pakt dus met zijn rechterhand mis. Zijn rechterhand.
oh. He was lucky he fell off before he got horizontal. Almost every single thing in gymnastics hurts from what I remember.
Dubbel salto, dubbel het groep. En hij valt. Ja.
Ah, that was a crazy move.
Das mãos, fazendo. Muito longe essa largada. Foi a largada, largou.
That was worth a second look. Oh, he got the old maximum tension. Ah! Oh! That was it again.
По крайней мере, он не шмякнулся вот локтями.
Dois côvados ligados, um esticado e um grupado direto. E aí, não. Falharam.
That guy just knew better than to hang on, I think.
Ele não.
Ah! He didn't know better. Okay. Yeah, that was worth it. Okay, let's talk about tetherball problems. Okay, so it takes two things. First, the mass is only supported by a cable. So we're not talking about something spinning around the floor on a string or something, only supported by a cable. And it has to be rotating in a, let's say the circular motion has to be parallel to the ground, you know, flat with the ground. That's why the example we just did wasn't a tetherball problem, because that was like a vertical motion, you know what I mean? In this case, it always has to be uniform circular motion. So that means that the tangential acceleration is always 0. And the way we're going to approach it is, you know, normally if we have a circle that's horizontal, the circular motion's like this, we would take a top-down view. But in these problems, we're going to take a side view. All the other steps are the same. Okay, so let's do a problem. So let's say you have an object spinning around a circle like this. And let's say the angle the string makes with the horizontal is 30 degrees. And let's say that the cable is, let's say it's 1 meter long. And let's say the mass of the string, the mass is 0.5 kilograms. And we want to know what's the cable tension. Oh, I need to give you one more thing. No, I don't. So we want to figure out what's the cable tension. And we also want to figure out what's the speed of the ball, or the mass. So first, let's make sure this makes intuitive sense. Does it make sense that we have enough information to figure out the speed of that mass? If someone was like twirling it around like this, and you increase the speed, what given value here would change? The angle, yep. So as it goes faster, that angle would get smaller, the ball would rise up higher. And if you did it slower, that angle would get bigger, it would drop down closer to the stick. Okay, so the view we're going to take is a side view. Here's the object. This angle's 30 degrees. We know that this has a length of 1. And what we're trying to figure out is this length. This is the radius of the circle. So that 1 isn't, we can't use that 1 directly. But that radius is going to be equal to the length of the string times the cosine of the angle, which in this case is 0.866. And now we need to figure out the direction of the centripetal acceleration. What direction would that point? So there are kind of two possibilities that most people would think of. One is along the cable and one is this way. And remember that in circular motion, it doesn't matter what the machinery is that's making it move in the circular motion. All that matters is the motion itself. So the circle's going around like this, and so the centripetal acceleration just points straight that way. Okay? Straight towards the center of the circular motion. So that's the centripetal acceleration. The magnitude of it is v squared over r, which we know is 0.866. Usually we've been able to, I think every time up until now, we've been able to come up with a number for the speed. But this is as far as we can go right now. So we'll have to solve for that later on. We'll just leave it like this. But we can represent this in vector components. The centripetal acceleration is in the negative x direction. I'll draw my coordinate system like this. So negative v squared over 0.866, and then 0 for y. These kind of problems are always uniform circular motion, so the tangential acceleration is 0. So the total acceleration is just negative v squared over 0.866, 0. And now we'll do a free body diagram of the mass. Because we're doing a side view, there's a weight force like this. What did I say the mass was? Half a kilogram? So this is 4.905 newtons. And then the cable force is this way. And it makes an angle of 30 degrees. So to come up with the components for that cable force, think of the tail of that force vector at the origin of the coordinate system. So that force vector is T times the cosine of 150 degrees, T times the sine of 150. And that is negative 0.866 T, positive 0.5 T. And so now put that in Newton's second law. And you have a cable force, negative 0.866 T, positive 0.5 T, plus the weight force, 0, negative 4.905 is equal to the mass times the acceleration vector, which was negative v squared over 0.8660. So first we can use the y equation to find t. So 0.5t minus 4.905 is equal to 0. So t is equal to 9.81. And then plug that into the x equation, and you get, let's see, negative 0.866 times 9.81 is equal to 0.5 divided by 0.866 negative times v squared. You can cancel the negatives. And let's see, you get 2 times 0.75 times 9.81 is equal to v squared. So that's, ooh, I can do this, watch. 14.715 is equal to v squared. Well, I can't do that square. So what do you get for b? 3.83. 3.83 meters per second. Any questions about that? Okay, so now you're ready to do any of the problems in the circular motion problems. So why don't you look at as many of those, work on as many of those as you can by Thursday. And if you have questions about them, I'd be happy to answer them before I start working on any new stuff.